Okay, so let's continue for solving the linear set of equations. And in fact, our next approach is Gauss elimination. We have seen it, but let me remind you how it works, in fact. Again, we have a set of linear equations and we want to solve them. Certainly, we have coefficients a11, a12, a13, and so on. And in fact, we have the unknown variables x1, x2, x3, and xn. We have the right-hand side of these equations, b1, b2, and bn. Now, in Gauss elimination approach, or method, let's say, we first choose one of the equations. And then we choose one of the variables. And we eliminate this variable from the rest of the equations in a step-by-step manner. So let's see how we do it. For example, we choose the first equation. Okay. In fact, the equation that we choose is called pivot equation. And then we choose one of the variables. For example, x1. The coefficient of the unknown that we choose is called pivot coefficient. So we have the pivot equation. In this equation, we choose one of the variables, let's say x1 in this case. And then the coefficient of it is a11, and this is the pivot coefficient. And what we do is we basically eliminate it from the rest of the equations. So how we do it? Simple. We first divide the first equation with a11. Okay. And then, for example, we want to eliminate it, the x1 from the second equation. And what we do is I multiply this equation with a21 and then subtract it from the second equation. I do the same thing for the third, fourth, and fifth. And as a result, x1, the variable x1 is eliminated from all of the equations except then the pivot equation. And it goes like this. So it is like this. Now this is the modified form of our first equation. So we first divide the whole equation with a11. As a result, the coefficient of the first variable, x1, becomes 1. Then we multiply it with the a21, the second equation. So this is the equation that we obtain then. If you subtract the second equation from the pivot equation, then what we are going to obtain is this. For example, for the first coefficient, the coefficient of the x1 becomes 0 automatically. And the coefficient of x2 is a22 minus a21 divided by a11 multiplied by a12, and that is multiplied with the x2. And it goes like this. For the nth variable, it is a2n minus a21 divided by a11 multiplied by a1n, and that's multiplied by xn. Of course, the right-hand side has to be modified because this term is subtracted from b2. And the second equation becomes like this. As you see, this equation does not contain any terms with x1. We can write it we can this modified equation, or the equation which we made an operation on it, like this. So this becomes our new second equation, a22 prime multiplied by x2 plus some terms plus a prime 2n multiplied with xn, and that's equal to b prime 2. So certainly b prime 2 is equal to b2 minus a21 divided by a11. A22 prime is this expression, a22 minus a21 divided by a11 multiplied by a12, or the nth term is this expression. So this is a prime to n, the expression inside the brackets. So this is what we do, and at the end, if we do it for all of the equations, for the rest of the equations, eventually x1 will be eliminated from all of the equations, and we are left with the equations without a term x1. This is called forward elimination. As a result, we end up with such system of equations. Okay, so the first equation contains all the terms. Then, of course, I choose the second equation as a pivot equation, and then I made the elimination of x1. Then I choose the second equation as a pivot equation. This will be my second step. And then I eliminate x2. And then I do the same thing. And I choose third equation as a pivot equation. And then I eliminate the x3s. From the equation. Here x1 is eliminated, here x1 is eliminated, here x2 is eliminated, and it goes like this. At the end, I'm left with the last equation. Since I have n equations and n unknowns, the last equation is left with the nth variable, and of course I can easily solve it, right? So xn, the value of the xn is bn, the n minus 1 modified. So the expression inside the parentheses just shows how many times it is modified. So the last equation contains only the xn term, and I can easily calculate it from here. And then what I'm going to do is back substitution. Now from this equation, I can calculate the xn, and then I put it into the previous equation, and then there I can calculate the xn minus 1, and it goes like this. At the end, in the first equation, if I go back to the first equation, so I can calculate x1. So this is how the elimination works. So basically, the nth variable can easily be calculated. As I said, with this expression, xn is equal to bn n minus 1 ann. That's also okay. How about how can I calculate the value? The right hand side, or any value inside the domain, any others. So be e minus 1 minus sum of the coefficients multiplied with the previous terms. Here j in the index, and it is from I plus 1 to n. So from here you subtract it from the BE, and then you divide it with the AII in the previous iteration, and you do it from n minus 1 to 1, as we said. So this is the back substitution step, basically. Once more, let me repeat it. So first I eliminate the x1. So what I do is I divide the first equation with a11, then multiply it with the a21 and subtract it from the second equation. This eliminates the first term from the second equation. Okay, so, and I'm left with such an expression. If I do it for the third equation, fourth and fifth, as a result, all the coefficients related with the first, all the terms related with the first unknown is eliminated from all equations. And as a result, I'm left with this equation in the second place. So this will be my second pivot equation, and my pivot coefficient will be a22 prime. Okay, and then what I do is first I divide this equation with the a22 prime, and then I multiply it with the a32 prime and subtract it from the third equation. And then from the third, I do the same thing for the fourth, fifth, and it goes like this. As a result, terms related with the x2 will be eliminated from the rest of the system. It will be the same for the third equation. You eliminate the terms related with the x3 from the rest of the system, and you go like this. And finally, you end up with an equation. In the last equation becomes a term, an equation with a single term, xn. Now I can easily find the value for xn. So basically it is bn n minus 1 divided by ann n minus 1. So here the superscript shows that how many times it was modified, or how many operations we made on it. And then what you do is now you find xn here and you put it in the previous equation, so n minus 1th equation, and then from there you find xn minus 1, and then it goes like this. At the end you find the x1 from the first equation. Now this is the back substitution step. So once you do the forward substitution, the second step is the back substitution. Of course, you can easily find the xn value, and the rest of the coefficients can be easily found by using this expression in the back substitution step. And look how many operations you make. You make n minus 1 operations here in the back substitution, whereas you again make n minus 1 operations in the forward elimination. Okay, so this is what basically the Gauss elimination is. And let's see how we can do it in a matrix by using a matrix algebra. So here we have the matrix, coefficient matrix. For example, let's say that we have a 3 by 3 square matrix, It is just for representation purposes. We have A11, A12, A13, A21, A22, A23, and so on. And then the right hand side of the equation, so we append it. So in the first step, we eliminate the all the terms below the first row. So what we basically did is, again, we divide these terms with A11, then we multiply it with A21, and then we subtract it from the second. So this becomes automatically 0. Now in the second step, what we do is, again, we divide this equation with A11, and then we multiply it with the A31. As a result, this term is eliminated automatically. Then we subtract it from here. Now all these terms become 0. Now I have to eliminate this one. So what I do is, this is already modified now with the operations. And in fact, then I divide this second row with the A22 prime. Then I multiply it with the A32 prime and subtract it from this equation. So this becomes automatically 0. This is the forward elimination step, and as a result, I'm left with the upper triangular matrix. Now next thing is to find the values. So I can easily find x3. x3 is equal to b3 prime prime divided by a33 prime prime. Now I find this expression. I will substitute it into the second equation. So I know the value of the x3 now. Of course, it is a prime 23 multiplied with the x3. Okay, so just correct it. Here it is wrongly written. This has to be, let me write it, x3. Here. So a prime 23 multiplied by the x3. This value has to be subtracted from b2 prime and has to be divided by a prime 22. This will give me x2. Now I know the value of x2 and x3. Again, I will multiply a12 with x2, a13 with x3, and then subtract it from b1, and we'll divide the whole expression with a11. This will give me the value of the x1. So this is the back substitution step. So here is the Poseidon code for the forward elimination. First, I have an iteration here. K is the outer iteration. So basically, we do the pivoting here. Sorry, we choose one pivot element and we do it from 1 to n-1. And then we have the I iteration. It is from k plus 1 to n. So basically we find the factor. So ak divided by ikk. Then we go for what we do is we subtract the second term, for example, 822 or 823 from the previous line, and it goes like this. This is the step. Of course, we can find the factor, then we can modify the right hand side with this line. Here what we do is we use the same array for b and coefficients, so this basically reduces the memory consumption of the computer, because we are not going to use those values again, and allocating new memory for the coefficients and for the right hand side is meaningless. This is the forward elimination. Then let's go for the backward elimination. Again, what we do in this case is we begin first finding the last variable, and then we do the following operations. So we begin from bi, we say that it is sum. Now, so first I put this value bi, and then I will sum the rest. Sorry, here, yeah, okay. So it is a multiplied by ij multiplied by xj. So I calculate the contribution of it to the sum, and then I divide this sum with the aii, and as a result the elimination is ended. Of course, the number of operations are important. So as you see, we have different loops here. We have outer loop, next inner loop, and we have the jth loop in the forward elimination. And let's see how many operations do we have. For example, we have n-1 here, and then we do it from k plus 1 to n, then j goes from k plus 1 to n, and here we make another operation. So basically we have n minus k operations here, division operation. In calculating the factor. For example, here again you do n minus k operations, multiplication, and then you do the subtraction, and here you do n minus 1 multiplication and subtraction. So all of these operations somehow consumes memory and takes time, CPU time, and CPU time is quite critical, especially if you deal with large problems. This is why we need these counts. So the outer loop k, for example, in the forward elimination, n minus 1. So in the middle loop, in the first, for example, outer loop, you go from 2 to n. In the second one, you go from 3 to n, and then it goes like this, and the last one is n to n. In the first loop, you do n minus 1 multiplied with the n, addition and subtraction. In the second one, for example, in the second outer loop, you do n minus 2 multiplied by n minus 1. In the kth outer loop, for example, you do n minus k multiplied by n plus 1 minus k, addition and subtraction. This takes time. And on the other hand, we have multiplication and division floating point operations. So flops means that floating point operations. For example, in the first outer loop, you do n minus 1 multiplied by n plus 1 multiplication and division. In the second one, it is n minus 2 multiplied by n, and it goes like this. And in the last outer loop, you do 1 multiplication and subtract 1 multiplication and 3 division operations, and here it is 1 and 2. So finally, we need to calculate the number of operations. Even though now the CPU times or CPUs are quite fast now, so they are capable of making gigaflops of operations. It is important in many cases. So as a result, we have, if we sum up all these things, we have n cube divided by 3 addition and subtraction floating point operations, and the remainder is order of n, so number of unknowns or number of equations, in other words, operations. This is what you do. And in case of a multiplication, again, you have n cube divided by 3 multiplication and subtraction operations, and in total, this is critical, Gauss elimination. In a Gauss elimination method, you do 2n cubed divided by 3 floating point operations. This is the total number of floating point operations you do. As you see, it increases with the number of equations, with the cube of the number of equations. So if you have 10 equations, basically you have 2000 divided by 3 floating point operations, and the remainder is order of n square. But if you increase it, for example, from 10 to 100, suddenly you see that it increases 1000 times. And this basically means that it takes a lot of time to calculate, to determine the unknown variables in a linear set of equations. So let's see, for example, when your equation has 10 unknowns, or in other words, if you have 10 linear set of equations, you have 805 operations, and the back substitution is 100, and total number of floating point operations are 805. And certainly the calculation gives us 667, which means that 87.85% of the operations are due to the elimination. When you increase the number of unknowns to 100 for forward elimination, you need to make 671,550 operations, and for back substitution you need 1000 operations. So total floating point operations is 681,550. So 2n cubed divided by 3, this is the approximation, is due to the elimination. So this basically means that you do 98% 98.53% of the operations for the elimination. And it goes like this for the 1000. Again, it's 6.67 multiplied by 10 to the power 7, and for the back substitution you need 10 to the power 6. It's n square for the back substitution, and total floating point operations are at an order of this. And certainly the total operations, floating point operations, 99.85% is due to the floating point operations. And so as you increase the number of unknowns, certainly the total time used for the elimination increases significantly. This is what it means. Therefore, Gauss elimination may not be feasible for very large set of equations. It depends on your computer source, basically. Certainly, Gauss elimination has some pitfalls. One is division by zero. So remember that we choose a pivot equation and then pivot variable, and we take the coefficient of it. Sometimes it can be zero. This basically means that you may have an error because the algorithm, the method, will divide the numbers by zero. Or even if it's not zero, sometimes it may be very small value. So this may cause some other errors, and you may end up with a illegal condition system. This is one thing. Since you do many operations, and in each operation you have some round of error, these round of errors accumulates in some cases and become huge and may be significant. This is another thing. And the third drawback is the coefficient matrix may be singular. So the determinant of it may be zero. You may have infinite number of equations, infinite number of solutions, which we have seen in the graphical method, or maybe there is no solution at all. So these are the drawbacks of the Gauss elimination. Of course, there are certain techniques which can be used to avoid such pitfalls. Okay, so there is another thing. You can use Gauss elimination for the calculation of the determinant. So you can easily, once you obtain the upper triangular matrix, you can calculate the determinant of the matrix by just multiplying the diagonal terms. As a result, you can easily calculate the determinant of the original coefficient matrix, D, or upper triangular matrix, like this. Okay, so this is one thing that you can use the Gauss elimination for. You can use it for calculating the determinant of the upper triangular matrix. Okay, how can we improve the Gauss elimination for the pitfalls that we have talked? You can use more significant figures. This is one approach, but in many cases we are limited with the computers that we use. Second thing is called pivoting. I will talk about it. And the third one is scaling. Now, in pivoting, what we do is very simple. Let's go back. Okay. Now, I eliminate, for example, the first equation. In case of a scaling, or let's begin with the pivoting first. Okay, so in case of a pivoting, for example, first I eliminate, or I want to choose one of the equations, right? And basically changing the places of the equations will not change anything. So what I do is very simple. If I want to eliminate the first variable, I just look for the whole system. This basically corresponds to the first column in the coefficient matrix. Let's look it from this 3 by 3 matrix. So this is my system of equations with the right hand side, and I want to apply the pivoting. So I just look at the, and in fact I want to eliminate the coefficients related with the x1. So I just look at the first column in this case, and I look at the values. I choose the largest one. For example, let's say that A21 is the largest one in this column. Changing the places of the equations will not change anything. So I put the second equation into the first row, and first equation into the second row. Now the pivot equation will have the largest coefficient in this column, and I will eliminate it from the first one. Now in the second one, what I do is, after doing the pivoting, for example, I have two equations, so A2 2 prime and so on, A3 2 prime and so on. It will go like this. Again, I will look for the largest of the coefficients, and changing places will not change anything. Changing the places of the equations will not change anything, and basically I choose the largest, I choose the equation with the largest coefficient of the corresponding unknown, and I put it into the second place, second row. So I change the places of it. So this is what the pivoting does, and this improves significantly the numerical accuracy. This is one approach. So the last approach is scaling. Basically, you can normalize the equation. So what you do is very simple. Again, you choose the largest you divide the whole equation, or better to say, you divide the whole equation with the largest coefficient. For example, let's choose one equation here. This is the equation, right? And the corresponding coefficients. And let's say that A12 is the largest value here. Dividing this whole expression, all coefficients, with A12 will not change anything. And I will divide it. As a result, the values become at an order of 1. And computers can easily handle such kind of an equation. So remember that large numbers, in order to handle the large numbers, you use different, we use different allocation in the memory. So you allocate, you need to allocate some of the bits for the mantissa, some of the bits for the exponent, and so on, for the sign, and many other things. This is to avoid such kind of an allocation. So you can do scaling. Of course, you can handle the complex systems. Sometimes you need to calculate the determine the variables with complex valued coefficients. As a result, the unknowns are also complex by means of numbers. They are also complex numbers. So here, for example, C is a complex valued matrix. Z is a vector of unknowns, and W is the right hand side of our equation, so it's again a column vector. Now, how I can solve such kind of a system? In fact, first thing is I can decompose the coefficient matrix into real and complex parts. Let's say that the real part is A and the complex part is B. Therefore, I can write the C coefficient matrix as A plus I multiplied with D. And then I can write the unknowns, Z. So Z is also a complex. So I can write, I can decompose it into real and complex part, X plus IY. And finally, W, the left-hand side, can be decomposed into the real and complex parts, U plus IW. So as a result, we have real and imaginary part, and real and imaginary part, and it goes like this. So we have real and imaginary parts. So we have the complex coefficient matrix, complex vector of unknowns, and complex valued vector of right hand sides. Now, if I multiply C with Z, okay, I will end up with such an equation: A multiplied with X minus B multiplied by Y is equal to U, because the real parts, this is A multiplied by, if I multiply A with X, this is AX. Now, if I multiply this term with this term, it will give me a real number. I multiplied by I is -1. Then this multiplication will give me this equation, and of course the right hand side has to be equal to the real part. What else? Now let's look at the complex part. Now in case of a complex part, I multiply I with IY. So it is A multiplied by Y, and then B multiplied with X. And this will form the imaginary part. As a result, B multiplied by X plus A multiplied by Y is equal to V. Now I need to solve this system of equations. I can use basically here two different approaches. I can form a global matrix and new large matrices. So remember that C has n variable. Now my matrix, my new matrix will have coefficients like minus B and B A. This will form my coefficient matrix. And certainly my vector of unknowns will be here. It will be X, and here it will be Y. And this has to be equal to U, V, and V. Now, as you see, since C is an n by n matrix, A is an n by n matrix, and B is an n by n matrix, so my modified coefficient matrix will be 2n by 2n square matrix. Again, X is a column vector of n, Y is a column vector of n. Now my new unknown variables will be 2n column vector. It is also the same. The right hand side will be a column vector of 2n. So this is how I can solve the complex systems of linear equations.